Okay, hi and welcome to the accompanying video for family of functions, which we're going to deal with examples. So in this video, we're going to deal with all of the stuff that we talked about in the previous video, but the examples of them. Right here is a quick reminder of what end behavior would look like if you need a quick reference for it. So they give you a couple of examples and they talk about what end behavior would be. Again, notice that all of these are polynomial functions. So what we're going to do in this set is I've got two done for you so that you can reference them as you go. Pause the video as necessary, but we're going to, one, sketch, not graph, sketch the function using Desmos. So our job here is that we're going to be given some function rule for, and then we're going to have to identify all the information as a sketch, which means that we've got a rough idea of what they should look like and what they should do based off what we see in the function rule. That's really kind of what we're after here. And then we're going to identify a bunch of the family traits that apply. Not all of them will apply. Some apply only based off the type of family of function that it is. So let's see if we can get through a couple of these examples here. Again, there are two, 1 and 2 I've done previous for you. So you can always stop, pause the video when I zoom out to full screen, and you can look through those and copy those down as well. Probably worth having so that you have some reference on these. But we're going to do 3 and 4. And you'll notice that 3 here, according to A, make sure that you've sketched both of these functions. I'm going to go ahead and assume that you did that. Go ahead and do that in Desmos because you can kind of see what it looks like, get a general idea. We are going to need some of the values, so make sure that you get a somewhat accurate sketch. So sketch those functions. You got those functions sketched. So it says name the function. That's going to be pretty easy for us. This one here you can tell is exponential because the variable is in the exponent location, whereas this one has a number in the exponent location. And this one additionally does as well, the 4 there. So this one's going to be exponential. Okay, so we've identified that as exponential. Next it says, what is the effects of the leading coefficient? So we're going to be looking directly at the coefficient, which is the number in front. And this one actually isn't the 2, as tricky as that seems. It's a 1 in front of it. That would be the part that's in front of there. So that's a positive 1. And that's really what we're looking for, is the effects of the leading coefficient. We're really looking for if it's positive or negative. That's all we're looking for there. So that's worth a note there on your part. And if it's positive, like this positive 1 there, you'll notice that I added a negative to 2 and I added a negative to 4. So those are negative coefficients. So if you want to see what happens there, then we'll deal with it. But remember that if it's positive or negative, the positive side, the right side goes up. And if it's the negative side, the right side goes down. That's what you need to remember there. So on this one, having a positive 1 for that lead coefficient, the right side, and if I grab my highlighter here, the right side of this function, right, is going up, and that's what you'd expect. If it's positive, the right side goes up, and it did. So let's go ahead and fill that in. Right side goes up. Okay, let's do both at the same time so we can have some contrast here. So looking at this function, I've got a negative x times an x, and we should know at this point that negative x times an x is going to make negative x squared plus 3. And the reason that we'd want to put those together is so that we can see that this, and we wouldn't get confused that this is linear, we can see this is an x squared term. And if it's squared, we know that this is going to be a quadratic. So we're going to write that in as quadratic. Now, let's look at that lead coefficient. So our lead coefficient this time is a negative 1. This one was a positive 1. This one's a negative 1. So that means if it's a negative, the right side goes down. Okay, and if we look carefully when our sketch, because we would have sketched this already, that our right side is indeed going down. So far so good. Let's see if we can answer the next question. It says identify the y-intercept. This is where your sketch will come into play. You'll need to be able to identify the y-intercept here and the y-intercept here. I've already marked this one as 3, and this y-intercept is going to be 1. Okay, and you would have to get that from your sketch or Desmos, or making a table of values. You'd have to make a table of values and plug in every y-intercept, and this is a key point to find out here. Every y-intercept has a 0 for the x-coordinate. That's how you identify the y-intercept in a table. So that would be the minimum way, that you'd plug 0 in here and calculate it, and you'd plug 0 in here and calculate it. I mean, do that really quick. Let's just do a little quick table here, right? if we do our expanded table where we evaluate in the middle, and then we get our f of x or our y value coming out, let's plug 0 in for this number 4 here, this quadratic. So if I plug 0 in, what I'm going to find is it's going to be 0 times, or negative 1 times 0, or negative 0 times 0 plus 3. And what does that equal? Well, that equals 3, because negative 0 times 0 is 0, plus 3 is 3. So you can see that that makes your y-intercept for you, the 0.03. So that's another way to find that. That's actually a really good note to make. Find y-intercepts. Let's put that here. Y-intercepts. Plug in input 0 to get the y-intercept. Huge note for you right there. That'll be a key piece. All right, so let's go back and answer that question then. So D, or identify our y-intercept in this case, if we plugged in 0 for this, let's plug in 0, 2 to the 0 power, and anything to the 0, I can't write, anything to the 0 power, let's do that again. Anything to the 0 power, if you remember exponent rules, is 1. So our y-intercept for this one equals 1, and our y-intercept over here for this quadratic was 3. Again, using the idea that we put in 0 and find out what it's equal to. That'll always give us our y-intercept. Okay, so E then says find any critical points if applicable. So that means any vertex. Well, you'll notice here, this one we talked lightly, kind of has one, but not something that we necessarily go and find. So if we can't find it, we're going to put NA. And you'll notice with the cubic here, additionally, it also has an NA, and so does the linear. However, this quadratic does seem to have a vertex. It happens to be where our y-intercept is. So we're going to label the point at which it's at. So it's 0 on the x-coordinate, but 3 up. 1, 2, 3 up. So our y-intercept for that one is 0, 3. Okay, F asks us to identify the domain and the range. Now, we lightly got into this in the last video. So for domain, for this one, we need to find the left bound. So remember, domain is along the x-axis. So how far does this function go? And this arrow says it goes on forever. How far will this function go? Well, if it goes on forever, over here is going to exist negative infinity. So that's my boundary. And since we can never touch negative infinity because it's always getting larger, we say it's not included. So my left bound for my domain, if I use my brackets, is rounded because I can't have it, and it's a negative infinity. Let's check to the right. So how far to the right can I go? You're like, well, Mr. Hallam, it looks like it stops somewhere right in here. But that's just not true. It's going up really, really fast, but it's still going over. So it still continues to go over. It doesn't really stop and turn up. There's not an asymptote here. There's not a boundary. Our asymptote for this one actually is along this line. It's our horizontal line right here along the x-axis. That's our asymptote. This is not an asymptote. It's really strange because it's going basically up, but it's still creeping forever that way, just mainly up. So that means if it creeps forever that way, that it's going to be to positive infinity. All right, so let's do our range then. Our range, let's switch colors. Our range then is how far down will it go? Let's find our low boundary. So it looks like our low boundary, since we know that there's an asymptote right here, that it's never really going to reach this point. It's going to get infinitely close. It's going to get really close to 0. It's going to get really, really small and really close to 0, but it's never going to touch it. So our low boundary is going to be the 0, but we're never going to touch it, so it won't be included. And then it looks like it goes up with an arrow at the top forever. So it's going to go up to positive infinity. All right, let's do that for our quadratic function over here. We'll switch colors again. So for our quadratic function, we're going to look for how far over can we see it, what's our low boundary for our x-axis. And even though it's going really far down, it's still going to the left. So, and it's going to go to the left forever because it has that arrow at the end instead of a dot. So if it goes to the left forever, it means that we can find it all the way on all these x values over to negative infinity. And you'll notice the right side's doing the same thing, especially since this has symmetry. It means that we can fold it over. So whatever the left side's doing, the right side's doing the same thing. So we can go over forever to positive infinity, and that function will keep sneaking over as it goes down. It'll keep going over. So then our domain for this one, it goes over to negative infinity, and we can't have it, so it's always going to be a rounded bracket for infinity, and positive infinity on the right. Again, another rounded bracket. So let's do the range. We'll switch colors again for the range. So for the range, we look to see how far down it's going to go. Well, this is easy. I can see both of these arrows sneaking down forever. So that means that we're going to go down to negative infinity. But how far up does this go on the y-axis? How far up can I go? It looks like 3 is the highest point that it's going to be. So we're going to use that. So our low boundary is negative infinity, and our upper boundary is 3. But 3, the line goes through 3 right here. See it? See it goes through there? It means that that's included. So we give that a square bracket. All right. Now we're going to do our first interval. So we're going to identify increasing intervals, and then we're going to identify any decreasing intervals. And that depends on the function. So let's look at the exponential function first. So if it's increasing, that means from left to right. We always read a function from left to right. That if we look, it's really close to 0, really close to 0, and then it starts scooting away from 0, and it's increasing forever, really. So from left to right, even though it's really small here, it's still always increasing. This function's increasing from one end to the other. So when we say an interval that's increasing, and this whole function's increasing, there's no intervals, the whole function's increasing. We say for the x coordinates, where is it increasing from? Where's the lowest point that it starts increasing? Well, in this case, it's negative infinity. And where does it stop increasing at? Well, in this case, it's positive infinity, because it keeps increasing forever as we go along the x-axis, and that's what we're looking for here for the interval. So this is an increasing function. The interval is increasing forever, so from negative infinity to positive infinity. Well, let's look at the quadratic one here. So this one, if you're very carefully watching, we have two different intervals. I have one interval from left to right, remember. This interval here is going up from left to right. As I go this way, right, it's going up. So this would be our increasing interval, and it would stop right here at 3. And then we have a second interval, which is decreasing, and the decreasing interval is right here. So it decreases from 3 down forever to negative infinity, or I'm sorry, towards positive infinity, because we're looking at the x values. So if we label this, we're going to have two intervals. Our first interval is going to be an increasing, okay, and our increasing interval is going to start at negative infinity, right? We can go over forever and find it. It's increasing forever from negative infinity all the way up to 3. And it's included, so it will get a square bracket. And our decreasing interval, okay, is going to start at 3, and 3 is included, and it's going to go forever to positive infinity. We're still sneaking over, just like the domain. Really, we're writing a mini domain in a mini range. We're writing, and what you should have with your intervals is that whatever your increasing interval starts at, and wherever your decreasing intervals, and you may have multiple of these, wherever they start and stop, it should cover the entire range. Because remember what domain and range and intervals are. They're the x and y coordinates to explain where it's doing something, a set of numbers. So the domain is what it's doing left and right, and the range is what it's doing up and down. When we look at the interval, since we're saying increasing, we don't care about the x value, or the y value. All we care about is where left and right is it increasing, and where left and right is it decreasing. Okay, and so you can see here, let's take a peek at these, that for our cubic, it starts high, and from left to right, it's always going down. So this will be a decreasing function overall. There's only got one interval. Same thing with a linear function. It's not very exciting. It starts low from left, and it ends high to the right. So it's forever increasing. So those ones are simple. But if you have a quadratic or even a cubic, cubics will have a couple intervals, right? It'll have some increasing ones, maybe a couple increasing and a decreasing. It just depends. It might have 3 intervals in it. All right. Let's go to the next part of the example, or the examples that we got here. We got 2 left. We get h, which is identify the asymptote, and remember, it's only applicable for an exponential. And how are you going to know where the asymptote is? Well, you're going to have to draw the sketch and see what number it's getting close to. In this case, we're getting really close to that x-axis. So when we write the asymptote, this is how we write it. We say y equals whatever number it's getting close to, and so in this case, it'll be 0. But let's look at a different case just so you have another reference. If this one came down like this, and it came down here, and let's say this was -4, we would say y equals -4, because it would get really close to -4. Okay, and that's how you're going to write it, y equals. All right, and this one is not applicable because it doesn't have an asymptote. Okay, there's no boundaries that it can't cross. It crosses all the boundaries. All right, and our last question then that we can look at is identify the end behavior. Again, polynomial only. So when we do end behavior for exponential, it really doesn't apply. And if you look at how we did it for the other functions, all we have to do for end behavior is identify if it's going up or down on the left and the right. Well, it's really easy when we started with the graph. What's this side doing and what's this side doing? It's going down and down. Now, if we take that back to the notes, though, and remember what we said about the notes, we said that we looked at the lead coefficient. So the lead coefficient right here is negative, which meant the right side went down. So what's it doing on this right side? It's going down. And it's even, so the other side has to do the same thing. So this side also has to go down. Okay, let's take a peek at this linear here. So let's look and see if we can do its end behavior. The coefficient, the lead coefficient, is positive, which means the right side goes up. And it's an odd degree, which means that they have to go in opposite direction, so the left side has to go down. So the left side goes down, and the right side goes up. All right, so we've covered all of those. You should be able to see how those are applied and how you're going to find the stuff. Really, don't forget you have to start with a good clean sketch. To find the y-intercept, you just plug in 0 and evaluate it to see what value comes out. Right side going up, right, is part of the end behavior, which we signify with arrows. Some functions we don't look at end behavior, other ones that we do. And most importantly, probably the part that you're going to have to want to look at a little bit more is the domain, which we're pretty okay with, right, going to a negative infinity. But the intervals are the portions of the domain where it's increasing or decreasing. So you do it the same way, you just have to find those boundaries where it switches from increasing to decreasing. And not all functions have it. Sometimes they're all increasing or sometimes they're all decreasing. All right, thanks for watching. We'll see you in class.